Hi everyone, we're going to go over section 13.4, mathematical induction. Mathematical induction is just a method of mathematical proof typically used to establish that the given statement is true for all natural numbers. So here are the steps to use the mathematical induction. So step number 1, check to see if the statement is true for n equals to 1. And the second step would be assume that the statement is true all the way up to some natural number n. And the very last step that what you need to do is that you need to show that or prove that the statement is true for n plus 1. If so, according to the mathematical induction method, then the given statement must be true for all natural numbers. So now you're probably sitting there going, what the heck? I mean, that's exactly how I felt when I was first introduced to mathematical induction. So think of it in this way. Have you guys all heard of dominoes? Not Domino's pizza, but like a domino effect. So dominoes are these little chips with the numbers on it. So suppose that you're going to make those dominoes stand up in a row, and suppose that the first domino is going to fall. So step 1, the first domino is going to fall. Then step 2, can you visualize the domino effect? If you push the first one, it's just going to keep falling and falling and falling all the way up to, let's just say, some number n. So that's just going to be our assumption. Assumption is that if I push the first one, for sure it's going to fall all the way up to n. And step 3, well, if the domino is going to keep falling up to n, your job is to prove that the next domino after n, which is n plus 1, is going to fall as well. So if the next domino falls, then what? All dominoes are going to fall. And that's pretty much how the mathematical induction works. Now, if I relate that to the mathematical induction, so step 1, prove that it is true for n equals to 1. That which is equivalent to first domino is going to fall if you push on it. Then step number 2, mathematical induction says that assume that the statement is true up to some natural number n. So that's the equivalent of saying that let's just assume that the domino is going to fall all the way up to some number n. And the third step, the mathematical induction says that show that the statement is true for n plus 1. So that's the equivalent of saying that assuming that domino is going to fall all the way up to n, show that the next domino is going to fall. And the conclusion of the mathematical induction says that if so, then the given statement is true for all natural numbers, which is equivalent of saying that if the next domino falls, then all dominoes must fall. I apologize if I made you even more confused by that analogy, but let's just do some examples so that you know what I'm talking about. So first example is that show that, or that's equivalent to saying prove that 3 to the n is strictly greater than n is true for all natural numbers. Alright, so let's do this. So I'm going to write it as proof. Now step number 1, what we need to do is we need to check whether the statement is true when n equals to 1. So let me write that out. Alright, so now let's check. When n equals to 1, is our given statement, is it true? So meaning, is 3 to the first, is it going to be strictly greater than 1? That's what you need to prove. Is that true? Yes, it is. So this is true. So the first step is done. Now, step 2, we need to assume that the statement is true all the way up to n. So let me write it. For some n is okay, or up to n is just fine as well. Now the third step is that assuming that 3 to the n is greater than n, is the statement true for n plus 1? So let me just write it. Is the statement and don't forget the fact that we're assuming that 3 to the n is greater than n. So to show that the statement is true for n plus 1, what we need to show is this. So what we need to show is that is 3 to the n plus 1, is it really strictly greater than n plus 1? Alright, so this is what we need to show. Before we start, when you do a mathematical proof, you cannot just give a specific value and show that the statement is true. So for example, let's take maybe n equals to 2 or something like that. So you'll be saying 3 to the third is, yeah, definitely greater than 3. But this does not prove anything because n can be any natural numbers. So let me just erase this and let's get started, all right? So let's check. Okay, so first of all, 3 to the n plus 1, that's same thing as what? 3 to the n times 3 to the first. Okay, but the thing is, look at our assumption. Let me see, where can I draw the arrow? Look at this assumption right here. We're assuming that 3 to the n is going to be greater than n. So this whole quantity, 3 to the n times 3 to the first, is going to be greater than n. So this portion is going to be greater than n times 3 to the first. Do you see that part okay? So if I write this nicely, then I would have 3 to the n plus 1 equals 3 to the n times 3 to the first. But 3 to the n is going to be greater than n. That's what we're assuming. So this is going to be greater than n times 3 to the first. Like, I guess I could call that 3n. But this inequality comes from the fact that we're assuming 3 to the n is strictly greater than n. So now what do we have? So we got 3 to the n plus 1 is greater than 3n. But let me just write this as a side work. But then isn't 3n same thing as n plus n plus n, right? So I'm going to replace this with n plus n plus n. Now meanwhile, don't forget what we were trying to show. We want to try to show that 3 to the n plus 1 is going to be greater than n plus 1. So far, all we have is 3 to the n plus 1 is greater than 3n, which is n plus n plus n. Now, we're going to have to use some tricks. Let's note that n is a natural number, isn't it? So n is a natural number, which means that n is always going to be greater or equal to 1 because natural number starts from 1, 2, 3, 4. And so forth. So do you agree that that means n better be greater or equal to 1? Then if I add another n to it, meaning if I add another n plus n, this is certainly going to be greater or equal to 1. Do you agree? So think of it in this way. Take n to be 2 or something like that. Then 2 is greater or equal to 1. Great. So that means what? 2 plus 2, which is 4, is certainly going to be greater or equal to 1. That's pretty much what I'm trying to say here. So with that said, this guy is going to be greater or equal to 1. So that means that this whole quantity is going to be greater or equal to n plus 1. So we have shown that 3 to the n plus 1 is going to be greater or equal to n plus 1. So therefore, all dominoes must fall, which means that by mathematical induction, the statement is true for all natural numbers. So you need to write that out. 3 to the n is greater than n is true for all natural numbers. So we are done with our first proof. And a lot of mathematicians write QED at the very end of the proof, which stands for that. Quod erat demonstrandum. Don't even ask me to pronounce that right. But anyways, let's take a look at another example. Now let's try this one. Use the mathematical induction to show that given statement is true for all natural numbers, which is 3 plus 5 plus 7 plus all the way up to 2n plus 1 equals n times quantity n plus 2. Alright, let's do this. So proof. Okay, so step 1, remember what to do? Is the statement true when n equals to 1? Alright, so let's check. When n equals to 1, our left hand side is just going to become 2 times 1 plus 1. So here we're going to have 2 times 1 plus 1. Does it equal to 1 times 1 plus 2? So this is you need to show that whether that's true or not. So what do we get on the left hand side? 3 equals to 3. So yes, therefore it is true for n equals to 1. Now let's go with step 2. Step 2, we're going to have to assume that the statement is true all the way up to n. Alright, so that means that we're assuming that 3 plus 5 plus 7 all the way up to 2n plus 1 equals to n and then n plus 2. So we're assuming this. Alright, now the third step. Is the statement true for n plus 1? And we got some work to do. So let's first write down what we need to show. So what we need to show is that is 3 plus 5 plus 7 plus, what was the nth term? 2n plus 1. And then 2n plus 1 plus 1 equals to n plus 1 times n plus 1 plus 2. So this is what we need to show. Alright, let's look at the circle too. We're assuming that this whole quantity right here, all the way up to 2n plus 1 equals n times n plus 2. That's our assumption. So we know that this is going to equal to n and then n plus 2. By our assumption. So now who's left over? On the left hand side is plus 2 quantity n plus 1 plus 1. So I'm going to distribute the 2n. So you're going to get what? 2n plus 2 plus 1, so it's 3. Sorry, so all I did was distribute, and then add the 1. Now from here, what we need to do is to work just on the left hand side. Just like when you're doing the establishing the identity, you have to pick either left or the right. So basically choosing the left hand side, and then show that that's going to equal to the right hand side. So let's work on this side. So this is going to equal to what? 2n plus, n squared plus 2n plus 2n plus 3, which is n squared plus 4n plus 3. This is factorable, so you're going to have quantity n plus 1 times the quantity n plus 3. Alright, so now let's just take a look at the right hand side of it. Isn't this exactly equal to the right hand side? Because look, this is same thing as n plus 1 and then n plus 3. So guess what? We're done. So we could say that this equals to the right hand side. Check. So therefore the statement is true for n plus 1. So I'm going to write therefore true for n plus 1. Check. Alright, so therefore by the mathematical induction, given statement is true. Is true for all natural number n. So we're done. How you guys doing up to here? Is it bad or kind of getting the hang of it? Just so that you get a little bit more comfortable, let's just do another one. Okay, we're going to do the same thing. Use the mathematical induction to prove the following statement is true. So what do we got? 1 to the third plus 2 to the third plus all the way up to n to the third equals 1/4 times n squared times the quantity n plus 1 squared. Feel free to pause the video and try this on your own if you like. Alright, so I'm going to start the proof right here. So step number 1. Is the statement true for n equals to 1? Okay, so let's check. When n equals to 1, what do we get? Well, n is going to be 1, so the only thing we have left is 1 to the third. So is 1 to the third. Does it equal to 1/4 times 1 squared times 1 plus 1 squared? I think that's true because this is 1 equals to, what is it? This one's going to be 2 squared, so that's 4. 4 over 4 is 1. So 1 equals to 1. Alright, so therefore, statement is true for n equals to 1. Now step 2, assume that the statement is true all the way up to n. Basically, what we are talking about is assume that 1 to the third plus 2 to the third all the way up to n to the third equals 1/4 n squared times n plus 1 squared. So this is our assumption now. Okay, now step 3, is the statement true for n plus 1? Okay, so let's write down what we're supposed to show. So i.e. is 1 to the third plus 2 to the third n to the third plus n plus 1 to the third. Is it going to equal to 1/4 n plus 1 squared and then n plus 1 plus 1 squared? No matter what, when you use the mathematical induction, you're going to have to use the assumption somewhere. So for this case, let's see, we already know that by assumption, these guys right here is 1/4 n squared times n plus 1 squared by assumption. So this is by 2. So again, what we're going to do here is Just like when we did the establishing the identity business, we're going to be starting from the left-hand side, and then we're going to show that's equal to the right-hand side. So I already know that this is going to equal to that by assumption. Now let's drop this guy down. We still have plus n plus 1 to the third. Let me just rewrite this because that orange box might be bugging your eyes a little bit. Okay, so this is what we have so far. Now, don't forget what you're trying to show. You're trying to show this is going to equal to the right-hand side. So let me see. So if I distribute, I don't need to distribute anything here. Okay, so this is what we need to show. What I just wrote down. So I think we're almost there. So how about this? We can factor out n plus 1 whole quantity squared. So let's do that. Do you see what I'm doing? We got the same factors here. So I'm going to factor out the n plus 1 squared, and then who's left over here? We have 1/4 n squared, and then plus n plus 1. Be careful with your algebra from here. Okay, so I'm just going to keep dropping down this n plus 1 squared. I'm not doing anything with that. Multiplying hereby. So now what I'm going to do is this. I'm going to factor out the 1/4 inside of the bracket. So if I do that, if I factor the 1/4 out, I need to rewrite what was in the bracket as n squared plus 4 times n plus 1. Can you follow my work okay? All we did was we just factor out the 1/4 from what's in the bracket. Now let's keep going. So this is equivalent to 1/4 and then n plus 1 squared. I'm just rewriting it in order. Now this portion here is going to become n squared plus 4n and then plus 4, which is 1/4 n plus 1 squared, and this one is going to be n plus 2 and then n plus 2, which is n plus 2 whole quantity squared. All right, are we done? What do you think? Look at what we're supposed to show. Look at the right-hand side. This is exactly the right-hand side. So it checks, so therefore the statement is true for n plus 1. I just double checked it. All right, so therefore, by the mathematical induction, the given statement is true for, oh, I'm running out of room, for all natural number n. That was an n, sorry. All right, so we're done. I know that doing a mathematical proof is not the easiest. If you've never seen a mathematical proof before, I know that it can be very overwhelming. And I feel that you're just going to get better at it by practicing it. But anyways, I'm going to stop here. If you have any questions at all, please let me know. Great job, everyone.